Hello and welcome to the bare metal programming series where we're building firmware for a Cortex-M STM32 microcontroller. It is episode 10 and it is in fact the first episode in the next couple of videos where we're essentially going to be putting all of the parts that we've been moving towards together, and that is to build the firmware update mechanism inside the bootloader. Now this is going to be kind of a few episodes in the making. Today we're going to focus on the bootloader side. In the next episode we can look at the client side, kind of the firmware update application, and finally we'll integrate those things together, fix the inevitable bugs, and actually update our firmware over the protocol that we have established. So let's not waste any time, let's get straight into it. So the plan for today is, as you can see, almost blank. We're just going to be writing a lot of code. The goal is to understand the communication and data exchange that's going to take place between the bootloader and the firmware, and then implement the bootloader firmware update state machine. So what is that? Well, we've kind of looked at it briefly before, but this is it, with maybe a small adjustment that wasn't there last time. So we're going to first wait for a sync signal, and the sync signal is just going to be a few bytes. It doesn't really even matter what those bytes are, but just a few bytes in succession that come through and kind of make it clear that someone is on the other end of the UART, and it's probably someone who's going to be trying to send us the right kind of packet. So it's a kind of knock. And the reason we do this and not just immediately start sending packets is because if someone starts sending packets, but then before we load up the bootloader, we end up in the middle of a packet somewhere, we have kind of no way of aligning ourselves. So this synchronization is there to basically just put a point in where we know that if we start creating packets from the stream, that it's going to be kind of synchronized. So that's the point of the sync. Then we will send our very first packet, which is the sync packet, and we'll send that to the firmware update application. And then we will wait for the firmware update application to request a firmware update. So you can imagine that maybe there would be a couple of different possible queries that might happen in the bootloader stage. Maybe the firmware updater can actually ask what the current firmware is and that kind of stuff. So maybe there would be a few paths through this different thing, and this is just one possible path. But in our case, we're just going to kind of have an almost linear conversation that just goes from firmware update request all the way to updating the firmware. So they'll send this update, we will acknowledge that, and not only acknowledge in the sense of our packet protocol, but acknowledge in that, yes, we accept your plea for a firmware update, let's continue. Then we will request the device ID. If that checks out, we'll request the firmware ID. If that checks out, then we will actually go ahead and erase our main application in Flash, and we'll send a trigger to basically begin receiving the firmware. And receiving the firmware will be a process of, hey, I'm ready for a chunk of data. We'll get a chunk of data, we'll write it to the Flash, and we'll send a kind of signal that says, I'm ready for the next chunk of data. So then when all of that is done, we will jump to the main application. And kind of at any given point, if any of these things take too long, and for too long we can really decide what that means, but if any of these things take too long, we will time out, and so we will end up just, in this case, just jumping to the main application, where that doesn't make a ton of sense if you've already erased your main application to jump to the main application because there's nothing there. It also doesn't really make a whole lot of sense if you haven't received the full firmware. But in any case, it's what we're going to do for now, because kind of we can take some incremental steps into getting a better and better firmware update mechanism. This will just be our basis. So to look at this kind of in other terms, this is kind of a sequence diagram. So this basically shows that we've got kind of two parties, and you can use these diagrams to just to map out kind of the communication, the protocol, things that happen over time. It's a good way of kind of modeling that, and you can have more than two parties. In this case, we have two parties. We have the firmware updater, which is the application, and the bootloader. So the firmware update the firmware update program is going to be sending in a loop the sync sequence. So it's going to be sending 4 bytes over and over again. And each time it will wait a second before it sends again. And the reason we wait a second is so that if we haven't received anything within that second, we're giving ourselves enough of a window to make sure that we really can synchronize. So we don't want to send just these packets over and over again, every, as fast as we possibly could, because what might happen is when we start sending the next few bytes, we've already sent a message that says, hey, we're synchronized, let's start talking in packets. And at that point, we've already messed up the packet buffer. So that's why there is a little delay here, and we'll stick around here for, 10 seconds maximum. And then if it doesn't work out, the firmware updater can say, I tried, but it seems that there's no one on the other side. But if that does succeed, then eventually we'll send a sequence observed packet from the bootloader, so that will come back. And then we're going to get a firmware update request. We will respond to that with a firmware update request accepted packet, kind of a response to that. Then we will send a device ID request. We will get a device ID in response. If those device IDs don't match, then we will not accept the firmware. This is basically the idea that this protocol could be used among multiple devices, and we can kind of address the devices this way. Then we have a firmware length packet. So we're going to request the firmware length, and that is the firmware updater's job to send that back to us. And that will be a uint32 value, so way more space than we actually need. And it will just tell us in bytes how many bytes that firmware takes up. And if it's too many, well, then we can't accept it. Then when that's done, we're going to go kind of into a new loop here. And that loop is that from the bootloader, we're going to be sending a ready for data packet. Like, hey, we're ready for data, you can send it. And then the application will send just 16 bytes of the firmware. So in this case, we don't have any kind of special marker on the packets. The packet is just going to be full of data. And it's still going to have the CRC, so we're still sure that that data is intact. But basically, once we get into that mode, we're just streaming data. So ready for data, send it, wait, write to flash, which takes a little bit of time, then send the next ready for data, get the next packet. And eventually, when we've got all the data that we need to receive, we're going to send a firmware update successful packet, and then we're done. We'll jump to the main application, and the firmware updater knows that there is nothing else to do. So that's the flow. That's how it's going to work. And I think we've got all the pieces to actually sort of get going on this, get ourselves going. So, all right. So this is our program as of now. So we're going to want to have our GPIO set up, uart comms, etc. We're going to want to have a timer, so we'll get that kind of ready. We're going to need some kind of while loop. So all of these pieces are kind of still there. We're going to need these parts, GPIO setup, jump to main, and we'll need all of this. And what I'm going to do for now is just build most of this stuff just here in this file, because we can always split it up afterwards. And I think it will make sense to just have the updater just here, and then we can always extract it later. Okay, so what I think I'm going to do is put all of the packet definitions for what we just looked at. I'm going to put them here in the comms header, even though comms I think is in it's in the bootloader, so it kind of makes sense. And what we'll do is that all of these higher level packets, so not packet RETX or ACK, all of these higher level descriptions, we'll prefix them with BL packet. So then this is going to be, I'm going to just open this to the side here, just to see what these packets we have. So we have a sequence observed. So let's just say sequence observed data 0. It doesn't really matter what we put here, so I'm just going to kind of choose some numbers randomly. So we'll have that one be hex 20, firmware update request. Oop, copying from the wrong place. So this is going to be firmware update rec request. We'll have that one be 31. Then we're going to have a firmware update response. That's us accepting, so we'll call it the response to this. 37. just choosing randomly. It really doesn't matter. You could try and be a bit smarter about this, but it's really not going to matter that much. We've got the CRC, so there's no real issue with it. Only you have to keep in mind that if you want to make more special meaning, you have to fit them in here. So eventually you'd want to have a big table somewhere. Okay, so the next is the device ID request. So device ID rec. Then we're going to have, well, let's make that 3C. And then device response, we'll make that 3F. This one will actually contain 4 bytes of additional information, so most of these are just like 1 byte packets. This one's going to contain a bit more. Okay, we'll see about that. I'm thinking too much out loud now. The firmware length. So this is firmware length request. Make that 4.2. The response to that will be in 4.5. And then we have ready for data. Ready for data, that one's going to be 4.8. Data packet, that's not going to have anything special because it is just a it's just a packet full of data. We don't need to tag that in a special way. And finally, the firmware update successful. So firmware update, let's just call it update successful. And that one will make it 54. Okay, so now we can use these constants. We'll save that. And what will we do? So we're going to have a state machine, essentially. So let's create a type definition for an enum, which is going to be the bootloader state t. And what states are we going to have? We're going to have the state where we are syncing. Then we're going to have a state where we are, why don't we open this thing back up? It's probably the easier way of doing it. We're going to have a state where we are waiting for an update request. Wait for the update request. We're going to have a state where we are dealing with the device ID. We're going to have a state where we're dealing with the firmware length. And then we're going to have a state where we erase the application. And then finally, we're in the receive firmware state, and then finally we're done after all of that. Okay, so then of course we can have a static bootloader state t state. This is just our state that we're going to begin in. That's going to be sync. And then we're going to need a few kind of in-between variables, and we can already think about those. We're going to need a firmware length, so when we receive the firmware length, we're going to keep that around, because when we actually come to receive the firmware, like, that's kind of the amount that we expect to receive. Eventually, if we get that much firmware, then we're done, right? We don't need to continue. So let's have a static uint32t firmware length, which we'll just set to 0 in the beginning. And these two states, bootloader device ID and firmware length, those states are actually going to have, you could split these up and we could have two states, but I'm just going to put it together like this. We're going to have the part where we request, and we're going to have the part where we receive that back. Maybe it makes sense to just have two states. So let's have a request state and a response state, a request state, and a response state. Okay, then we're going to erase the application, receive the firmware. So we're going to need something to keep track of where we are in terms of writing the firmware, how much firmware have we received. So I think we'll just call that bytes written. So we'll use this to basically know where we're writing into Flash. And this might be all of the in-between data we need. We of course need to define what our device ID is. And again, I'm just going to pick this randomly, and I'm going to say our device ID is hex 42. Why not? So we'll have device ID be 1 byte. This would allow the system to support 256 different devices. And if you wanted to extend that, you could just, it will be very, very straightforward to extend that to any number you want. So effectively, I think if you had something like a uint 16, you would have more than enough to support whatever range of devices you probably had available to you. Okay, all right, so syncing, yeah, we need those sync bytes. So just need to define all this stuff right there. So the sync sequence 0, let's say that is the byte C4, then the index 1 is going to be 5, index 2 is going to be 7E, and 3 is going to be 1, 0. So all these are is just 4 numbers that we expect to get in a row. And we're going to use a kind of shift register to deal with this. So that's another piece of state we'll need. Static uint at sync sequence. And there's going to be 4 bytes here, and they just all start at 0. So what we're going to do is we're going to receive these 4 bytes. And let's not even talk about it, let's just write it. So we have to initialize the timer, but let's do this first. So we're going to have a loop. And the first thing I want to do in this loop is just check if we are in the sync state. So we're going to use a switch statement as well, but this is easier to handle if we do this one separately. So if we are in the BL state, if we're in the sync state, what we need to do is to check if we have any uart bytes available. If we've got some data, then we are going to just like shift all of this data down. So the newest received piece of data is going to go into index 3, and we're just going to shift all of the rest of those down. And then eventually, well, after we've shifted, we're going to check if we have the sync sequence. That's it. That's how it works. So the sync sequence at 0, that becomes whatever was at sync sequence 1. Sync sequence 1 becomes whatever was at sync sequence 2. Sync sequence 3 becomes whatever was at, sync sequence 2 becomes whatever was at sync sequence 3. And sync sequence 3 becomes whatever we have available in uart. So we're going to read a byte from uart. Okay, so then we've read the sync sequence and we can just check it. So I'm going to have a bool is match, and that will just, we're just going to check a bunch of these things. So sync sequence 0 is equal to sync sequence 0. Is match is equal to is match, and the next one. I'm just spreading this over a couple of lines because it's kind of easier to work with this way. Okay, so at this point, is match is going to tell us if we have the sync sequence. So if it is a match, then at that point we need to do something. And what we need to do is to send the synced packet and move to the next state. So in order to construct a packet, well, let's come out here and make a comms packet T. I'm just going to call it packet. And yeah, we're just going to use this packet to both receive stuff and send stuff. We only ever need to really be dealing with one packet at a time. We don't need to keep them around. So one piece of data here is enough for us. And what we're going to do with this is, well, the way in which we construct packets, if we come into comms.c, we actually have a couple of places where we construct some packets in this way. And what I want to do is to just make a function. I want to do two things. I want to expose this function so we can use it. Comms is single byte packet. And I want to create a function called comms create single byte packet. That will be the easiest way to create single byte packets, and that will just allow us to very easily just like write the data into a packet for one thing. We can use it here as well. So first of all, I'm going to be jumping around in this episode because we need to make a lot of little changes here and there. So if anything isn't clear, just try to follow it through and then go back to sections that don't make sense if they don't make sense. So we're going to expose this function now. So just take away the static part. And we're going to have another function here called void comms create single byte packet. So then it's going to have the same interface basically. Is we're going to, instead of it being const, we're going to just create a packet with this here. And this is another little change that I'm going to make. Another little change that I'm going to make is something that I was kind of considering doing in the previous episode, but didn't end up doing it. I'm going to bring in the standard string library, because that contains a few functions like memcopy and memset. And I was a bit hesitant about bringing it in. I wrote this custom comms packet copy function, because I wanted to first experiment to see what would happen if I brought this in, and as it turns out, it's completely fine, and it will just generate the correct code. It won't even bring any special functions in. So what we're going to do is just replace our instances of comms packet copy with memcopy. So I'm just going to use memcopy, and memcopy first takes the destination and then the source and the size of the thing we're copying. So the we have this the other way around, which makes it a little bit confusing. So the destination is the packet buffer in this case, and the source is the temporary packet, and the size is just size of comms packet T. So we're just copying the whole packet. So then we can get rid of this one. So then again, copy, yeah, so we have these two other places where we use it. So this is the destination, right? This is the packet is the source. So this is our source. Our destination is then this one, and definitely shouldn't make that mistake. This is our, just check the signature again because it always gets me confused. Destination source. So we're going into our last transmitted packet. From this packet, this is the size. Okay. And again, when we read, then we're going the other way around. All right. So our destination is packet, and our source in that case is the packet buffer. Yeah, checking every time, because this is the sort of change that you make where you really mess things up. Okay, so that is what we need to do for that. And the reason that I wanted to do this is because I also want to use memset. So when we create a single byte packet, like, we don't quite need to do all of this stuff. So let me these ones. So kind of, we're going to create a length 1 packet. We're going to use this byte, but we don't actually really need to do this stuff, this setting to FF. What we can do instead is just memset the whole packet to be FF in the beginning. So the void pointer that we're going to is just our packet. The value that we're going to write is ff, and the size of this is size of comms packet t. So we're going to memset the whole packet to ff, then we're going to set the length field, the byte field, and compute the CRC. Okay, so then we can actually just use that here as well, right? We want to create an RETX packet. We pass that in, and we pass the byte. Should have just done this the first time around. And for the ACK packet. Okay, that's good. Then we don't need comms packet t anymore, so that goes away. And now we actually only have these, it's all public functions. All right, so now we can roll ourselves back to over here, and we're actually ready to send a packet. So what are we going to do here? We're going to call comms create single byte packet. We're going to send in our packet, and we're going to be creating BL packet sequence observed data 0. Yeah, I actually want to rename that to sync observed. Right, so we're going to create the packet sync observed, then we're going to write the packet. So we've observed the sync, we tell the other side about that, then we're going to change our state to be the wait for update request state. Okay, so that's good. So then we will simply continue after this, so no matter what happens. So this is just a really simple, straightforward case of us doing this. And the reason that I put this state separately is now we're sure that we will never get to the next line if we haven't already synced. So then we can run comms update. Because comms update, of course, is going to sort of take control of our UART data stream. It's no longer really legal for us to read UART packets because, UART bytes, because comms update is expecting to receive those. So now we can do this, and we can have a switch statement on our state instead. And I'm going to scroll up, and I'm just going to copy all of these, and I'm going to dump those in. Okay, so we've got kind of a little point for all of our states here. We don't need the done state, because that's going to be kind of our breaking out of this loop condition. So while state not equal to BL state done. So if we're ever done, then we'll just leave the state. And before we get to all of this, let's set the timer up. So simple timer setup, and we're going to set it up so that it's going to be end timer. Our wait time is going to be let's make some constants for this. So we'll have like a define default timeout. And this is going to be in milliseconds. And what's a good time here? Who knows? Let's say maybe 4 seconds is a good timeout, or 5 seconds. Let's say 5 seconds is our default timeout. So we're going to do that. And are we going to auto reset? No, we don't need to auto reset, I think. Okay, so we're actually going to want to use this while we're in this state, right? So if there's no data available, I guess we want to do this in two ways. Just trying to think what's the best way of doing it. So if there's no data available, we're going to want to kind of check our timer, but we're also going to want to check our timer if it wasn't a match. So what we'll do is we'll say if simple timer has elapsed, timer, then this was great, but it wasn't going to work out, so we go state equals bl state done, and we're going to break out of this whole thing. And likewise, on the else here, we'll do the same thing. And what we'll also do is, I'm just thinking now, we should also probably kind of inform the other side that we're kind of giving up. We can at least try to inform them. So what I'm going to do is I'm going to go to comms here, and let's add one more packet, which is going to be something that we kind of spoke about previously, which is going to be our NAC packet. And this NAC is going to be like a protocol level NAC. So when we send this, it's basically saying, like, whatever you did, it's not good. We're not continuing. We can't recover from this. At least that's the way I'm going to set it up for now. So if the timer elapses, then we will create a single byte packet, which is our NAC, packet NAC, and we'll send it, and then we're going to be done. And we're going to do that here as well. You can see we could kind of wrap this stuff up into a little function that might be kind of just like handle timeout. Yeah, but in the case that we didn't time out, we also want to reset our timer. So we don't want to we don't want to have only 5 seconds for this whole process, because it might take longer than 5 seconds. So what we actually want to do is to reset the timer between each successful state. So if it's a match, great, we will simple timer reset and timer, and that's going to reset our timer for the next go around. Okay. Alright, so what do we do if we are waiting for an update request? Well, this is kind of straightforward, right? We need to check, do we have any packets available? So now, comms packets available. Do we have any packets available? If we do, and of course we've got our case if we don't. Maybe I'm already going to make just this little function for static void. Static void check for timeout. And we won't take any arguments, and we'll just do this stuff there. Which means that we need to make our timer, we need to bring it up here as a kind of module level static. And I guess we need to do the same thing with our packet, because we're going to use the packet. So let's do that. All right. All right, so instead of this little piece of code, we're going to just check for timeout. Same thing here. All right, so if we have packets available, we're going to receive a packet. So we will do comms read, and we'll pass in our packet. And we're going to check, is this the packet we're looking for? So we can use comms is single byte packet. It's going to be this packet. And the one that we're looking for is BL packet firmware update request. So if it's a firmware update request, great. We can send our response and continue. If it's not, that's going to be a failure mode, and we're just going to want to do this stuff. So maybe we can use static void yeah, these are bad names. Maybe I'll change it shortly. We can actually do this stuff here. And we can use that same function down here for if it is not the one that we're looking for. So that will also end up leaving this whole situation. But if it is a successful packet that we're looking for, then we can we're going to create the response. So comms create single byte packet, and it's going to be BL packet firmware update response. It's basically that we're accepting this. We're going to comms write that packet, and we're going to move to the BL state. BL state. What is the next state? The next state is device ID request. Okay. Good. So then, in device ID request, what do? Well, we are going to send a request, which is basically going to do this step. Here, we're going to send a single byte packet, which is the BL packet device ID request. Write the packet and move to the response state. And then in the response state, it will look kind of similar to this one, because we're just going to need to receive packet. So if there's a packet available, read it, check if it is the bootloader device ID response. And actually, in this case, we can't use the comms is single byte packet because we expect there to be more than just a single byte in this packet. So let's make a static bool is device ID packet. And we need to pass in the comms packet t pointer to the packet. We're not going to make any changes, so let's make it const. And basically, like, we can use almost the same logic that we do inside the is single byte packet. So it's going to be basically this, except we don't expect there to be, well, in a device ID packet, we expect 2 bytes, and we expect data 0 to be BL packet device ID response, and then from I equals 2 up until data packet length, we expect it to be empty. So this is how we can check for a device ID packet, and let's just make the same function but for the firmware length. So a firmware length packet will actually have 5 bytes because we're going to have the byte that identifies it as a firmware length packet plus 4 bytes for a uint32 size. So in this case, we expect this to be a firmware length response. Yep. And we're going to go from index 5. Okay, so I think those two are good, and we can now use them in the state machine. So, if this is a device ID packet, great, let's get the actual device ID and validate it. So, if it's a device ID packet, and the packet.data at index 1 is equal to our device ID, in that case, we will send, we'll just change state at this point because we're going to do the request. So we will go to the firmware length request state. Otherwise, we fail bootloading and we check for a timeout in the other case. Oh, in all of these places, we also need to reset the timer. That's something we need to be doing. So, of course, yeah, here we always need to be checking for timeout, even in this case. But basically, we only need to check for timeout when we don't have a packet available, because either we're going to fail because it's a packet that we don't expect, or we don't have any packets available, we're waiting, and that's where we could time out. So in this case, we will in every case, reset the timer. I'm going to reset it here. We're going to reset it here. Although this is effectively like, you know, a few microseconds afterwards, if that. So maybe we don't need to do it. I'm going to do it anyway. And then here, in this case, we will want to reset. When we do the firmware length request, that's going to look pretty similar to this. So let's grab that. Again, reset the timer. We're going to send a firmware length request. Send the packet, and then move to the firmware length response state. Firmware length response will look pretty similar to the device ID response. So let's grab that code. Read the packet, check if it is a firmware length packet. And in this case, I think I'm going to already, regardless of what the actual contents of this packet is, excuse me, I'm just going to read the firmware length out. So the firmware length is going to be, we're going to have to reassemble the bytes here. We're going to assume it's sent in little endian. So that's just the choice I'm making. It has to be sent in little endian, and we have to read it as little endian. So the first byte that we receive will be the lowest byte in the number. So this is going to be packet.data1, and then we're going to OR that with packet data 2. Packet data 2 needs to be shifted up by 8. Packet data 3 needs to be shifted up by 16. And packet data 4 needs to be shifted up by 24. That will give us our firmware ID. Firmware length, rather. So then we can check that here. We can check and firmware length is less than or equal to the maximum firmware length. So what is the maximum firmware length? Well, the maximum firmware length is define max firmware length. That is going to be the flash size. Do we have a flash size here? I'm not sure if there is actually just a flash size defined in libopencm3. Define. That's the flash. That's the signature. I think that's only related to this idea of the signature size. So I think we can read it from there, but I think what I'm going to do is just include it in here as a hard number. So 1024 times 512. That is the maximum for flash size, minus the bootloader size. So then this gives us the maximum size that our firmware could be. Max firmware length. So if we got a firmware length packet and the firmware length that they send is less than the maximum size that we have available to us, or equal to it, it could be also equal to it, that is great. We can move on to the erase application state. We're going to reset the timer, and then in erase application, well, we know what we can do here. We're not going to check the timeout here, so we don't even need to do that. We are going to run bl flash erase main application. That could take a couple of seconds, and on the sending side, we'll actually account for this. We'll wait a little bit longer here. So maybe we give 5 seconds as our general timeout. Maybe we want to give like 8 seconds or 9 seconds here, because that flash erase can sometimes take a little while. It shouldn't take 9 seconds, but just for the sake of giving everything enough time, we'll be a bit lenient there. Then we can reset the timer, so because we want to wait until after this point to give it the latest time. And then we're going to change our state to receive the firmware. And this is where kind of all the magic happens, right? So in this state, we're going to be doing basically this, more or less. We're going to be checking to see, do we have packets? We're going to read the packet. But in this case, we're going to read that packet, then we're going to write that packet's data to flash. So how do we do that? We write to flash by saying bl flash write. We're going to pass an address. So the address is just main application start address plus the number of bytes we've already written, right? That starts at 0. And I've already been through this, of course, because we called this bytes by offset before. But in this case, I'm going to leave it as bytes written because we're writing these bytes to flash. So the main app plus the bytes written. And the data we're going to write is packet.data. So that's already a pointer to an array here, or it's an array, so it is a pointer in terms of C's degradation rules. And how many bytes do we have in this packet? Well, if you remember in the packet format video, we talked about some of the the pluses and the minuses of this format. We talked about the fact that this length field is actually a byte, but there are only 4 bits required to say how many things we have in the packet. So I'm going to actually decide to make use of that, to actually commit to using those 4 bits properly. So we're going to use the idea of 0 representing 1 byte in the packet and 15 representing 16, right? So we're offset by 1 because we should always send at least 1 byte in a packet. So we're not going to waste that one number that we have. So what we're going to do here is, for this length, it's going to be the packet.length, just the bottom 4 bits, which is the f and plus 1. So that's how many bytes we really have in this packet. And that will avoid a kind of malicious problem that could happen in this case, where someone actually writes that there's a lot more than 15 or 16 bytes in the packet. And to avoid having a kind of buffer overflow issue that would happen reading beyond this packet into the main application, we're going to avoid that. So I'm going to make a uart, just make it const uart packet length, which will just be this. And then we'll use that here, because we're also going to immediately use that underneath, where we do the number of bytes written is plus equal packet length. And then what we can do is that if the number of bytes written is greater than or equal to if it's greater than or equal to the firmware length, then we know we're done. So in that case, we will move to the done state. All right. So every time we get a fresh packet, we're also going to want to reset the timer, because we're still going to be checking for timeout in all of these situations. So we always want to check for that. Okay, that actually covers this whole thing. It's always good to have a default state. So let's just make the default state be that we set state to be BL state sync. So just go to the first state if you somehow have an invalid state. Doesn't really make a difference. And I'm almost half tempted to say go to the done state if you're in that. Okay, so that actually, assuming that I've done this correctly, this should be the main implementation. But we have a couple of things that we need to do. So one of them is that we need to do this tear down. So let's think about this. We have a bunch of things that we end up setting up. We have the system setup, and inside the system setup, we set up the clock. So this is fine. We don't need to do anything with that. But we also do the sysdig setup where we create an interrupt and we set the counter enable, all of these things. We kind of need to, we need to undo this. So what I'm going to do is to create a another function here, which is going to be called system teardown. And in system teardown, we are going to RCC. We don't need to do anything, but we need to undo this sysdig stuff. So we're gonna, first of all, we're gonna disable the interrupt. So sysdig disable interrupt. Then we're gonna disable the counter. And then I think we can reset the whole thing. No, maybe sysdig clear. I don't actually know what this function does. It clears the counter value useful for a well-defined startup. That sounds like what we want to do. So let's clear it. Is there just a sysdig disable in general? No, just the, all right. I think this is all the teardown we need to do in this case. And we're gonna have to say that we have this function. So let's go into the header file, system.h, system teardown. Great. What else do we have? We set up GPIO. That's something we do in this file. So let's have GPIO teardown. And in GPIO teardown, we're going to disable the clock to GPIO-A. So peripheral clock disable. And before we do that, we need to do everything kind of in the reverse order. I'm going to change the mode of these pins, not to the alternate function, but to the analog. Analog is kind of like the default mode for pins, right? So it's the lowest power mode. So if we set them back to analog, it's kind of like we're resetting these pins. So that's how I'm going to handle the GPIO part. Then we have uart. So inside uart, here especially we need to do some stuff. So uart teardown. So the ring buffer, don't think that needs anything special. That's just setting up a data structure. We don't need to do anything with that. What we do want to do is kind of do everything in reverse. So we want to do USR disable, USR 2. Then we want to maybe we need to first disable the interrupt, disable the RX interrupt. Then we want to disable the whole NVEC. Do that kind of here. I'm trying to think. Do I need to do this in a particular order? And then we need to disable the peripheral clock. Okay, that's looking good for that. Let's put that in the header. uart.h setup teardown. And then comms, does comms need anything? I don't think it does, because we don't have any kind of, like, apart from the UART, we don't have anything running there. So I think we have enough now to tear this down. So what we're going to do is that when we, well, one thing I didn't do here is that if we're done, we need to also send the message that says that bootloading is complete. So let's do that here quickly. Comms create single byte packet, BL packet, update successful, send it, and then we're going to do our teardown. So we do it kind of in the opposite order. So let's just grab all of those things to do teardown. So it would be comms teardown, but we don't have anything to do with comms. So then we would do UART teardown, GPIO teardown. There's something we need to keep in mind here, right? Which is that we're trying to send some UART data. There is no way we're going to send all 18 of these bytes before we hit this function call. So we actually want to wait for a certain amount of time before we're done. If we're doing this really properly, we would we would actually check to see that the UART is finished sending all of the data we expect it to. But I'm going to do this the kind of the stupid way, which is I'm just going to wait 150 milliseconds because it feels about right. Like it should be more than enough time, but it won't feel like a long time for the user. So then we can tear down the UART, we can tear down the GPIO, and we can tear down the system stuff that we set up. And then we're good to jump to main. So I believe that this actually should be everything we need. Let's just give it one more look through. So these are all of our states. This is the information that we have. Well, a good smoke test here, right, is always to just try to compile. So we run make. This file is deleted. Close editor. That was kind of weird. This file was deleted. Okay, so what do we get here? Declaration of packet shadows a global declaration. That is true. So in this case, I want to call. It's not actually a problem. Like it's actually fine for this to be the case, but let's just call it the temp packet. Then we need to make sure we change it in the right places. So temp packet. It should be easy enough to find that. Just guiding myself around by the red lines on this this thing here. I'm sure I'm going to miss one, but that will at least be easy to find. All right. It's weird that this is coming up here. I don't know why it's coming up there. All right, so it appears to build correctly. That doesn't mean that it works, but it does mean that it built correctly. So I think that we're looking pretty good here. So what are we going to do when we actually come to write this on the application side, right? Well, it's going to be really similar, actually. I think it will be a little bit, we'll structure it a little bit differently because in TypeScript we'll be able to have an async function. We'll be able to just await results, and that means that we don't actually need to have an explicit state machine. Excuse me. So we don't need to kind of just move through specific states. We can just say, hey, await sync with bootloader, and then we'll do that, and then we'll have functions for all the different things. But I think we'll end up just building the same kind of little bits and pieces that we did here. So just in the comms, we have these, single byte packets and these kind of checks. We'll build all of that kind of stuff there as well. And of course, we'll need to actually read a firmware file, strip out the bootloader stuff, and present all of that information to the bootloader over UART. But I think we're good. So I'm going to call it on this one. I'm sure that there are a couple of bugs, but we'll find them, we'll squash them, and we'll get them up and running in the next episode. So I hope some of this has made some sense. If it hasn't, I know that this one in particular has been really fast and really focused on just writing the code. There's quite a lot of code to write for this particular part of the project, and it's important that we get it right. But if some of it hasn't made sense, if you're wondering why a particular piece hasn't made sense, just try going back to it and seeing if it clicks. Look at the diagram as well. But if it doesn't make sense, then please leave a comment below, and please feel free to join the Discord channel where you can ask a question directly and I can try to answer it. Other than that, I'm just super excited now to get to the next part where we write the main application and where we write the client side of this, the firmware updater, and we get these two things talking to each other. I think it's going to be so cool when we finally get the first firmware update running on this thing. So I'm really excited for that. I hope you are too. Thank you for watching, and I'll see you in the next one.